Okay, let's start the LED. That is chapter 5 in our textbook. And this is my outline. First, I will give an introduction from the historical review of the LED. And we will show the material system because we need to have the blue, green, and red to achieve the white emission. So they use a different system, including the nitride system and phosphide system. And after we have the LED, then after we have the red, green, blue LED, then we can have the white LED. And we will show you some example about the electrical property and optical property. So the input is the electrical signal, the output is optical signal. And we will go to the fabrication, which include the epitaxial growth and the device fabrication. Then we need to consider about the light extraction efficiency due to the total internal reflection in such a device. So we will spend some time in extraction efficiency enhancement. Then we will go to the package and to provide the electrical paths, optical paths, and thermal paths. And also that is helpful for light extraction efficiency. Then we will show you some application which include display and the lighting. And we also cover some of the application here in chapter 4 when we talk about the backlight of the LCD by using the LED. Okay, so it's an introduction. And so the Nobel Prize winner in physics in 2014, that is awarded to Professor Isamu Akasaki, Professor Hiroshi Amano, and Professor Shiji Nakamura. And due to their excellent research for the invention of efficient blue LED, and that is very important for the blue LED, especially that is not a very conventional semiconductor, especially semiconductor material, especially for the epitaxial growth. And we will discuss this later. And also, we will show you that is we call that is a wide bandgap semiconductor, and so they have different interesting applications, not only in the optoelectronics, but also we call that is the third generation semiconductor, and they have many applications in the different areas. For example, the high frequency area and also the high power applications. Okay, here are some references. So this is chapter 5 in our textbook, Introduction to Flat Panel Displays. Also, in this chapter, we also refer to we also use lots of the figures from this book, Light Emitting Diodes by Professor Fred Schubert. And he is also the advisor, a very famous advisor, a famous professor, and to have a great impact in the LED industry. Also, we use this as our reference book. That is by Professor Shiji Nakamura, and he is also the winner of the Nobel Prize, as we said before, in 2014 in physics. And also we use this as our reference book about the solid-state lighting. Okay, so from the history viewpoint, actually the LED, that is light emitting diode. Light emitting diode means actually in this structure that is not diode, but anyway, they just observe when you supply the electrical power and some light emission was observed. So for example here, they provide 110 volts, and they can see some light. There are some yellow, green, or orange, or blue. So that is that was observed back to over 100 years old. But actually, at that time, they don't know what's the reason. So they say, oh, maybe the electromagnetic wave or something like that. And that is at that time the LED was a Schottky junction diode. Is still diode, okay? Not a PN junction diode. So it's a very long history. We say over the 100 years. Oops. Okay. So that's a long history for the LED until now, after 100 years, and we can see different applications. So as we said, in 2014, the Nobel Prize was awarded to the invention of blue LED, which also imply in the early stage, we don't have the blue, and we have green, but the efficiency is not so good, was not so good. So for the early application for the LED, you can see the color is red, okay? So that is an indicator in the mainframe. It's a computer mainframe, and you can see the function is okay or not to verify the function of the PCB printed circuit board, or you can put as the backlight of the phone or some calculator or watch or so. And the problem is the power consumption is very high, and it was an issue until the 1990. And they have the very high brightness and high efficiency application of the aluminum, gallium, indium phosphide LED, which provide a high performance LED, high performance red LED. And we can have the long wavelengths, or we say that is the narrower bandgap, which include a red or orange. We can have some yellow or yellowish green, maybe green, but the efficiency is very low. So starting from the 1990s, and there are lots of the large signage or displays, we can use the LEDs, but we don't have blue or green at that time, about 30 years before. And as we can see, about from the 1994, 95, and to 2000, and at that time there's a strong, lots of invention and a strong growth. And to the green and blue, we call that is short wavelengths or the wide bandgap nitride LED, gallium indium nitride or indium gallium nitride LED. So that we can have that, we need to have red light and also the green light, right? So we can have the traffic light, and we can have the automotive light, and we have large display as well. We need to have the green and blue. So why the material? We need a different kind of material for different kind of the light emission. Okay, first of all, let's go to some fundamental about the epitaxial growth. So we need to, when we want to have some if we want to have specific light emission wavelengths, then we need to choose suitable materials. And we will see that the material must be grown on a substrate. And for the substrate, they have a certain lattice constant. Okay? So if the material grow upon the substrate have a larger lattice constant, so the epitaxial growth, they will experience compressive strain. Okay? On the other hand, if the lattice constant is smaller than the substrate, then they will feel the tensile strain. So both strains are not so good in terms of epitaxial growth. That means if we have we have the strong strand here, and then accumulate the strand that will result in some dislocation. And this kind of dislocation, and they will result in the problem because the repeated structure does not exist. There are some discontinuity here, and that will result in some defects. And defects results in the non-radiative decay. We will talk about that, and that will reduce the efficiency of the light emission. Okay, so that is important. So let's see the band diagram, band energy versus lattice constant for the long wavelength system, which we call the phosphide system. And we use aluminum, gallium, indium. It's a group 3 material, and they combine with the group 5 system, phosphide. So this we call the quaternary because there are 4 elements goes together on the substrate of the gallium arsenide. Okay. Okay, so let's see. You can see some point here. Here's an indium phosphide. We call that a binary. We have a group 3 and group 5. They can make form the semiconductor, as we said that in chapter 3. And also we can have gallium phosphide here, aluminum phosphide here. And for the indium phosphide, the lattice constant is here about 5.8686 angstrom. Okay, and the energy band gap is about 1.35 electron volts, and that is about 900 nanometer for the wavelengths, so which is the infrared. And also for the aluminum phosphide and gallium phosphide here, they have the much lower, smaller lattice constant and wider band gap. Okay, so think about in the periodic table. So actually, the aluminum and gallium, aluminum is the smallest atom, okay, compared with gallium, then the indium. So from the top, from the upper row to the bottom row, okay, from the top to the bottom. So that means aluminum is smaller, the atom is smaller compared with indium, although they are group 3 materials. Okay, so when you increase the size of atom, of course they have the larger lattice constant because they are bigger. Okay, consider, so the phosphide here is the same, but aluminum, gallium, indium is larger than gallium is larger than aluminum. Okay, at the same time we can consider that because the lattice constant is smaller and the bonding energy is stronger, so the bond is stronger, so that will result in the higher band gap energy and corresponding to the shorter wavelengths. Okay, so the trend of this figure, I mean the energy band gap versus the lattice constant, is like from the top left to the bottom right in this direction. And here, so we just say indium phosphide, gallium phosphide, aluminum phosphide. We call that is binary, because that's we call this compound semiconductor with two different atoms. So we can mix indium phosphide. In indium phosphide, we put some gallium inside. So we can substitute indium side with some gallium. So along this line is we put gallium into the indium phosphide and increase the gallium composition. Okay, so we can tune the lattice constant as well as the band gap. Okay, so along this line we can tune the band gap from the infrared into the red region and to the orange region, and even the yellow region, the green region. At the same time, we can also tune the wavelengths by incorporate aluminum into the indium phosphide. So that is along this line. Okay? So that we can use, that is called a ternary. That is called binary. B-I-N-A-R-Y. So that is ternary. T-E-R-N-A-R-Y. And so that we can tune the band gap by the ternary material. And also, you can see, oh, well, it's green, but why there's no color or is a dash here? That means it is in the red gap, in the red band gap, which means maybe we talked that in chapter 3, which means the minima of the conduction band does not coincide with the maxima of the valence band in K space. So which means the result is actually the radiative recombination is not efficient in this region. So which means we can use the green, we can use as green or yellow or orange or red with this material. But remember that although we can tune the material, we can tune the composition with the, for example, indium gallium phosphide, aluminum indium phosphide. But we do not have this kind of the substrate, as we said in chapter 3. It is not easy to obtain the crystalline substrate, especially for the ternary or quaternary. So we can have the binary substrate, and a common substrate is the gallium arsenide. And gallium arsenide have a lattice constant at 5.65. So we can choose, we can tune the aluminum, gallium, and indium ratio to achieve red, orange, yellow, and green region, and lattice match to gallium arsenide to avoid the lattice mismatch and avoid the defect formation, and to obtain the better quality of the epitaxial growth, so that we can achieve the high brightness and high efficiency long wavelengths, because we can cover only the long wavelengths LEDs. So that is the reason we need a quaternary. Quaternary means we need a 4 element put together. Okay, so for the long wavelengths material, that is the previous aluminum gallium arsenide system, we do not use that anymore. So as we can see here, if we want to have the lattice match condition for the aluminum gallium indium phosphide system, so actually the Y value, which means the composition of aluminum and gallium, the summation of aluminum and gallium is almost equal to the indium. Okay, so the 0.5 and 0.5. And we can change the ratio between aluminum and gallium. Then we can tune. So when we change the X value, then we can tune the energy band gap. But we cannot have the higher aluminum concentration. Otherwise, it will be kind of indirect band gap. Okay, so as we can see here, if we have a larger X value, then we can have the wider band gap, but there is a limit, okay, because they will fall into the indirect band gap. So that's the meaning we can successfully obtain the long wavelength LEDs. And this figure shows you the direct and indirect band gap. So as I said before, the minimum of the conduction band coincide with the maximum valence band gap at the K space, so that the electron from the conduction band goes to the valence band and emit the light. On the other hand, if that is an indirect band gap, actually, because the photon provide a very small momentum, so we need to conserve the energy, also conserve the momentum, so that we need another trap to assist this transition. So the efficiency is pretty low. And also, when the minima of the conduction band is similar for the direct and indirect uh, uh, band gap, and actually at that time the efficiency is lower. So which is planned actually when you go to the red, from the red to the yellow or green, actually the efficiency drops a lot. Okay, so another issue is we need to have some material system to cover the short wavelengths, or in other term, we need to cover the high energy wavelengths. High energy portion. So that's green and blue. So that is a nitride system. So the same, we can use aluminium and gallium and indium nitride together. And as we can see here, gallium nitride itself is emit the light at UV. So if we want to push to the longer wavelengths, we need to incorporate some indium inside. And if we want to have the shorter wavelengths, then we need to have some aluminum inside. Okay, so if we put some gallium, we put some indium into the gallium nitride, then that is along this line, and we can cover from the violet, from the UV to violet to blue to green, yellow, even to the red. So that's very good, right? So we can have the whole visible spectrum. The second exciting thing is actually in this diagram, that is all the red band gap. Okay, so what's the problem? The problem is actually we cannot find a suitable substrate. Silicon carbide is here. Zinc oxide may be okay, but we also need to consider about the crystal structure. And so that is a problem. We don't have the suitable substrate for the gallium nitride system. And the other thing is indium nitride. Actually, they are easy to have we call the indium aggregation. So indium is kind of metal. So if the metal aggregate, that will absorb the light. So which means for the gallium nitride system, when you increase the wavelengths, and the efficiency drops a lot. So that is an issue. Okay, so let's see that is from the Nobel lecture from the Professor Amano. So, for example, as we say, if you want to grow the substrate, or we call the bulk growth, if we want to have the diamond is precious, right? Diamond is expensive, right? If you want to have the diamond, you need 50,000 ATM and a very high temperature, over 1,000. It's 1,200 degrees C. But if you want to have a gallium nitride substrate, it is possible. Yeah, you need a comparable high pressure, 45,000 ATM, and much higher temperature, over 2,530 degrees C. So that is very difficult. But fortunately, we find or we can say it's interestingly, we find a sulfide. And the latest mismatch with gallium nitride is 16%. So it's a huge number compared with the conventional semiconductor, as we said, phosphide system for the long wavelengths. And typically, latest mismatch should be less than 1%. But for the sulfide, it's larger than 60%, but it's still worse. So it's amazing. So how could it possible? So actually, there are some kind of the buffer layer growth in the nitride system. which means we reduce the temperature. They have the low temperature buffer before the epithelial growth on the sulfide substrate. So for the sulfide substrate, if we have the low temperature growth, we have the lower temperature, and they can have the pretty uniform film, although that is not so good quality. And we can increase the temperature followed by the gallium nitride growth, epithelial growth, and they will become uniform. It's interesting. And if we omitted this buffer layer and use a high temperature to grow the gallium nitride, and they will have some we call the island growth. That's not uniform, and we cannot use that for the semiconductor devices. So it's a very interesting growth mode or interesting invention. So make it possible to have the gallium nitride epithelial growth thin fins. And the other thing, there are many interesting characteristics in gallium nitride. The other thing is the p-type doping. Okay, so in chapter 3 we said, we can incorporate some group 2 or group 2 material atoms into the 3,5 compounds, and they can achieve the p-type doping. However, when we put for example magnesium into the gallium nitride, we found there's no p-type doping. The whole concentration is still very low. Zinc here. Okay, so this is the also the Nobel lecture of the Professor Amano. So they found actually if you irradiate the electron beam on the p-type material, and you can greatly increase the photoluminescence intensity, because you can activate, looks like an activate of the p-type material. So actually at that time that was that was mainstream for the blue LED at that time using the gallium nitride. So in that meeting presentation, only 4 people, including the Professor Akasaki. Professor Akasaki is Professor Amano's advisor and chairman in that room. So at that time that was a mainstream, but that is very important findings. So but at that time actually they just provide some energy here, and but they don't know what happened, or electron beam is not suitable for the mass production. So Professor Nakamura used another method to achieve the same thing, and he explained the phenomena. So actually for the gallium nitride, okay, so gallium is the orange sphere here, nitride is a blue one. So when we grow the epithelial layer, that is, we use MOCVD. We will discuss this later. And the gas, the source we use is NH3 or ammonia. So we use the NH3 to bring the nitrogen atom here. And for the p-type material, we use a group 2. So for example, here is a magnesium. Okay, so interesting is actually the hydrogen will passivate the magnesium so that they cannot provide the whole. Okay, so the hydrogen is a source of the passivation of p-type gallium nitride. So passivate the magnesium here, so that he found to remove the hydrogen, you can use a higher temperature to break the bond between the magnesium and hydrogen, so that we can achieve the p-type gallium nitride, so that we can have the p-n junction. So p-type is an issue for the gallium nitride material. So as we can see here, with the thermal annealing to break the bond between the magnesium and hydrogen, and they can achieve the much lower resistivity after the thermal annealing. And the resistivity decrease means increase in conductivity, so that we can have the p-n junction. Okay, so that's two breakthrough. And so for the nitride system, so the band gap is, we can vary the indium concentration in indium gallium nitride and to achieve a different band gap. And also for the indium gallium nitride system, 3 means group 3. So here's indium gallium. Of course, you can put some aluminum as well. So they are the red band gap for the whole range. So that is a good thing. So which means from UV to red is possible, okay? But when you go to the longer wavelengths, the indium cluster, they form the indium aggregate. They will form the indium cluster due to the indium aggregation. So that will be an issue, and that also limit the nitride system from the blue to the green. Okay, so here's an example. You can determine the composition of indium gallium nitride, and they can have the different emission wavelengths. So you can see the this example. Okay, so gallium nitride actually it is not a conventional semiconductor, and they have the many interesting characteristics. One of that is that they have the spontaneous polarization for the gallium nitride, and especially for the Wu-Si structure gallium nitride. So that is a Wu-Si structure, and actually they have the hexagonal plane on the XY plane, and also they have the Z plane. So we can define some axes A1, A2, and A3 and C. So anyway, if we gross the gallium nitride layer by layer, so the red is the nitride, gallium, gallium. If the top surface is the gallium, so we call that as a gallium polar. On the other hand, we call that as a nitrogen polar. So they will result in a different polarization, okay? Because the bond between the gallium and nitride is ionic bond, okay? So it's a gallium, is a nitride, and inside here is cancelled, but here we can see the gallium and nitride is a polarization toward the bottom, is toward the top. And we found out actually if we gross, we don't have to gross from this direction. We can try to tune the growth condition, and we can growth on this direction or this direction. Then we can try to find some surface, okay? They can have the lower polarization or even the no polarization. We call that a non-polar. And if the polarization is smaller, we call the semi-polar. We can find some possibility here. So for example, here's a semi-polar phase, and here's a non-polar phase. And this is the spontaneous polarization. And there are also some piezoelectric polarization. Okay? So the electric polarization results from the strength. So as we can see here, due to the as we said, the lattice mismatch is an issue, and they will result in the piezoelectric polarization. So that will result in, as we can see here, there are some misalignment because there are some polarization here. So you can see it's some dipole here, and they will result in the split in the wave function inside we call the quantum well region or the active region. Sorry, here's active region, not the quantum well region. So you can see the misalignment in the space that will result in the reduce of the overlap integral. So that will result in the result in the reduction in the radiative efficiency, also the optical efficiency. So that will be the problem. So as we can see here, if we have the polarization under the different excitation, so when we inject, for example, electron, the electron will go to the lower energy of the conduction band, so they will go to this side. On the other hand, for the valence band, they will go to the other side. So they are not at the same places. I mean, in the spatial domain, they are separate. So that means the efficiency for radiative recombination is lower. But if we increase the excitation, we have the higher current density, then they have the balance. They can have the higher radiative recombination efficiency. So that is an issue for the gallium nitride LED. So anyway, so right now we can see actually for the LED we have the very strong increase in efficiency. So here the y-axis luminous efficacy, as we said in chapter 1, and for the x-axis is the year. So as we said before, for the longer wavelengths, starting from the different kinds of the material, gallium phosphide, aluminum gallium arsenide, or so, but really the strong increase is happened in about the 1990 to 2000. There's aluminum gallium indium phosphide material is a quaternary material, and they can achieve about 100 lumi per watt. And on the other hand, starting from the 1992, 95, something like that, then they have the strong increase in the green and blue LED. And here are some record for the white LED, and we can see here they can achieve the over 300 lumi per watt for the white LED. So that's very high efficiency. And actually we mentioned there's an upper limit for the LED, which is 683 lumi per watt, and that is only for the monochromatic light. That's at 555 nanometer. So you can think about that. What is the upper limit for the white LED, and what is we will show you that there's a trade-off between the CRI and the efficiency. Okay. So as we said before, we have two systems. One is a phosphide system, one is a nitride system. And for the phosphide system, actually the efficiency is much higher in the longer wavelengths, and that decrease toward the shorter wavelengths, because that's direct to indirect transition. Okay. On the other hand, for the nitride LED, that is very efficient in the UV and also the blue region, but to the green region, actually the efficiency drops due to the epitaxy growth becomes difficult due to the indium concentration increase. So sometimes we call there's a green gap around the 550. Fortunately, actually 550, we say the human eyes is very sensitive in the 555 in this region. So actually that is not a big issue, although the efficiency, I mean the external quantum efficiency, is not very high for the nitride and the phosphide LED systems. Okay, so right now LED actually we can cover the whole spectrum range, and we can mix the different colors. So to achieve the white emission, we can have the blue and yellow LED, and we can use blue plus yellow phosphor, and actually that is what we use. I mean from the most common way to achieve the white light. And also we can use RGB, of course. We can use 3 LED or use phosphor as well, and also use a UV LED. That's another approach. And Also, we can use more than 3. At least 3 is good for the RGB, and we can put another cyan or so. The 2 parameter we said we need to consider about the efficiency, and as well as if you use for the lighting application, then you need to consider about the CRI. So there are some pros and cons here. So the dichromatic LED with phosphor, that is a commercial success, but the color rendering is not so good compared to the tri-color LED. And for the phosphor-based approach, they have a very good color stability because of the light time. For the blue and the yellow, maybe there's a different. But here, the yellow comes from the blue excitation. So actually, the lifetime is not the color stability is not an issue. And for the phosphor-based approach, there are some stock shift energy loss. What does that mean? That means actually, for the yellow photon comes from the phosphor, okay? And the phosphor comes from the blue photon to excite the yellow phosphor. So here the phosphor receive the high energy photon and release the low energy photon. So that we call the stock shift. Okay. So so if we want to avoid the stock shift, we can use a blue and yellow LED. Okay. So as we say in chapter 2, if we choose the lambda 1, for example, the blue LED, if that is 380, then we can find the other wavelengths too, 568 or something like that, and to achieve the white line. White line we can define maybe the illuminant E with the CIE 9031 coordinates at 0.33, 0.33. And if we increase the blue wavelengths, and we also increase the yellow wavelengths as well. But when we choose the 2 wavelengths, and actually we can achieve different luminous efficacy. Okay, and here we also consider about they have a different 4-width and half maxima, 2 KT or 5 KT or 10 KT. 10 KT means it's broader. Okay, 2 KT means it's narrower, it's sharper. So as we can see here, if the lambda 1 is about 440 and lambda 2 is about 563 or so, and we can achieve the highest luminous efficacy, and that is also the upper limit of the luminous efficiency is about 400 or so. And if you have the narrower 4-width and half maxima, they can have the high efficacy. But the problem is, so we can see here, luminous efficacy, we can achieve over 400 lumen per watt, but with the narrower bandwidth, a narrower light emission, 4-width and half maxima. So that means if you want high efficiency, then you will have the narrow emission band. So that will result in the lower color render index. So that is good. That is good for the display, maybe white, high efficiency, that's good. But the color render index is not so good. For the lighting application, it's not so good. Okay, so here shows you the trade-off, fundamental trade-off between the CRI and the luminous efficacy. And actually, for the blue LED pump yellow phosphor, and that is a quite simple model. For the LED, you input the electrical power, P0, then then will go to the photon. Part of photon will go out as the blue emission, and part of the photon will pump your phosphor, and to the combination of the blue and yellow results in the white emission. And the most common way until now is use the phosphor. That is inorganic phosphor. So consists of the Yttrium, aluminum, and gadolinium, and when changing the different ratio, X and Y value here, and they can slightly changing the emission band. So for example here, if we increase the Y value, Y value is 0.5, is 0, okay. So here 0, if we increase the Y value means if we put more gallium into aluminum, then we can see the red shift, okay, from here to here. Blue shift to the shorter wavelengths. So it's a blue shift in this composition. On the other hand, if we increase the X value means we put more gadolinium into Yttrium, then we can have the red shift in this condition. So, okay, so we see this figure. So if we have blue LED here, emit the light maybe 460 or so, then we can tune the YAG composition here, our phosphor composition, then we can achieve this area for the light emission. Okay, if you choose one phosphor, maybe we can have this line. If you choose this composition, we can have this line as well. So we can achieve different color. And so practically we use this kind of configuration. That is our gallium nitride, and we fill some phosphor. So there are some blue emission goes out, and there are some photons they will interact with. They will be absorbed by the yellow phosphor, and they will emit the yellow emission as well. Okay, so that is a common way, and if you use tricolor, and you can do lots of the calculation or simulation. As we can see here, if we have the narrower band gap, and actually the line here shows the lumen per watt, you can possibly have the higher lumen per watt. For example, here is 360, but here only 340. And here we can choose different wavelengths. For example, the lambda 2 is a green one, lambda 3 is a red one, and we can fix the blue one. So that one, so for the narrower, we can have the narrower line width, we can have the higher efficiency. For the broader one, we can have a lower efficiency. But consider about the CRI, color rendering index. This one is much lower. This one is maybe 75 or 80. But this one we can achieve the 95. So that is possible. There are lots of engineering work. You can tune the lambda 1, lambda 2, lambda 3, and obtain different lumen per watt and the CRI value. So that is a white LED. Okay, so think about the electrical property. So actually, the LED is a PN junction. So the ideal PN junction means when that is a forward bias, and that looks like a short circuit. When that is a reverse bias, that looks like the open circuit. But of course, actually that is not so ideal. So which means we need some turn on voltage, okay? So here is, for example, maybe 0.7 volts we can turn on. And we will see that actually the turn on voltage depends on the material system. If that is a wider bandgap material, for example, the nitride system, then we need a larger turn on value. And that if that is for the phosphide system, and that will be shorter. And also for the reverse bias, actually they have some leakage current, not zero but close to zero. But if that is very large reverse bias, and there was some breakdown. But anyway, basically for the reverse bias, we don't care about the characteristic here for the LED applications. Okay, so in the LED or in all kinds of the electrical devices, we use several fundamental equations. And in LEDs, actually, we want to show you in the following several pages to derive this IV characteristics based on some fundamental equations, which include drift diffusion equation, include the Poisson equation, as well as the continuity equation. But anyway, we can see here that is the result of the PN junction. Actually, the I and the V here in the forward bias, which means when the V is a positive value, and actually it's an exponential increase for the current when we increase the voltage. Okay, so we can use approximate expression here to describe for the forward bias. And for the reverse bias, when V less than 0, and actually the current is almost approximately to the IS. It's called a saturation current, and it's a very low level. Okay, it's a constant. Okay, so this figure shows we use a PN junction, so which means we put the p-type material, and that is in contact with the n-type material. Okay, so at the boundary of the p-type and n-type material, actually because the n-type material, there are lots of the electrons. For the p-type, there are lots of holes. So holes and electrons, they are free. So the hole in the p-type material, here is still p-type, they will recombine with the electrons in n-type material. So if they recombine, then they will leave immobile a negative charge here. So as we can see here, from the right to the left, there's electric field. We call that a built-in electric field inside the PN junction. Okay. Okay, so this figure shows in the view of the Fermi level. So Fermi level of the p-type material is at the bottom, and the n-type material is close to the conduction band. When you put together, and Fermi level we can regard it as the water level. So if you put two material together, the water level should be the same. Okay, so that results in the bending. So the band will bend like that, and here's the electric field from the right side to the left side. Okay, and we call this region, we call the depletion region, because there's no free charge in this region. And here shows an derivation of the equations, and I will let you know very briefly that is called the diffusion current, which means if we have the N is the electron concentration here, so if there are some gradient in the electrons in space, and actually the electron will diffuse from higher concentration to lower concentration. So the electron diffuse, this process we call that will result in the current. Okay, from the higher concentration to lower concentration, we call that is the diffusion current. And the other thing is the electron will respond to the electric field. So we call that is the drift current. So we can write the equation of the electron current and hole current based on the drift current, drift contribution, and the diffusion contribution. So we call that is the drift diffusion equation, or we call the current equation. And also we can calculate the voltage drop or the built-in voltage inside the depletion, and follow the Poisson equation. Okay, so here's the Poisson equation. It's derived from the electromagnetic wave, so that is the first principle equation. So as we can see here, the electric field is related to your carrier concentration. Okay, so it's a bound charge. So for example, it's a p-type, it's an n-type material. So here's depletion region. So here's a positive bound charge. Here's a negative bound charge. So the x-axis is the space. For example, the x, and the y-axis in this equation is a rho x here, and so that will result in the electric field like that, and that will result in if you integrate the electric field, so that will become the voltage. So it's a voltage like that. So we can obtain the voltage of the built-in potential. So that there are some detailed calculations, so that we can have the relation between the depletion region and the built-in voltage, and that is related to the epsilon s, and also the Q is a constant, and the acceptor donor concentrations as well. And epsilon is permittivity. Okay, so that so in reverse bias and in forward bias, and we will have the different voltage value, so that will result in the wider depletion region in the reverse bias, and for the forward bias, and actually depletion region will decrease. Okay, so we don't use the reverse bias region in LED, so I just omit it. And also it's a quick example. You can try to calculate yourself how to obtain the depletion region and also the built-in voltage if you have these material parameters. Okay, so what happened for the forward bias? So for the forward bias, actually we provide the voltage or current from the P to N. So that actually we provide more holes from the P and more electrons from N. So that will result in the hole concentration increase. Okay, and electron concentration increased, and we can increase the current. And here, then after some equations, and I will not go to the detail here, then we can obtain this value. So you can see here the current and the voltage, there's a relation is proportional to the exponential V. So that will be the exponential increase. Okay, so that is the equation. We just saw it. So that is from the fundamental equations, and we can increase when we increase the voltage, and we can increase the current as well. So that is the basic JV characteristic for the LED. So here, actually, for the different materials, and that is JV characteristics for the forward bias with different kinds of the PN junction. And for the germanium, the band gap is very small, and the turn-on, you can see here, is very lower diode voltage. if we increase the energy bandgap from the germanium 0.7, silicon 1.4 or 1.1, gallium arsenide 1.4, gallium arsenide phosphide 2.0 to the nitride, gallium nitride 2.9, and you can see the driving voltage increase. And actually, it's approximate to the energy bandgap over the E, and we will show you why. So here is the bandgap energy versus the forward voltage at, for example, 20 milliamp. So you can see actually it's almost along this line. Okay, so which also tells us if we have the if the material with wider bandgap, then a larger bandgap, then we need to use a higher voltage to drive it. Okay, so that is the JV characteristics for the LED. And when we use for the LED, actually the characteristics we want to use is the Hall and electron recombine to generate the light. So for the conventional LED, if we increase the forward bias, and actually we reduce the barrier between the P and N type material, so the Hall will go from the P type go to the N type, and electron will go from N type to P type, so they will recombine and to give the light. So we call that the homo junction. But if we supply too many holes, so hole maybe go from the anode and go to the depletion region, go to the N-type material, possibly they will go to the cathode, and that will result in the leakage. So one way to avoid that is we introduce the heterojunction material, which means, for example, here we have the larger bandgap of the N-type material and the smaller bandgap of the P-type material. So the hole will go inside, and that is blocked somewhere here. Okay, because the P-type material, they have larger bandgap compared to the P-type material, and the electron will go confined in this region, so they will have more probability to meet each other for hole and electron. Okay, so in other words, we can spatially confine the carrier in this small region. Okay, and that is a heterojunction, or we call it single heterojunction. Heterojunction means we use the two kinds of the material with different bandgap. So the other thing is we can use double heterojunction. Okay, so we can have the P-type material and N-type material with a larger bandgap. So we can see the energy bandgap is larger here compared to the energy bandgap here. So the hole will go here, go down here, and that is limited in this region, and electron will go down here and limited in this region. Okay, so that is common practice for the LED right now, and that is we create a region that is with a lower bandgap for light emission. And the other thing is when we reduce, we can change the composition to change the bandgap of the material, and we will do that. So for the heterojunction material here is about 1 micron. Okay, but if we can have the smaller feature, for example, less than 100 nanometer, then we can quantize the energy, so we can tune the emission wavelengths, and that is a very efficient. So that provides us another possibility to tune the emission wavelengths, and also they can also change the density of states, but I will not talk that too much. And also that is the example for the indium gallium nitride. As we said before, there are some misalignment here, but if we have some quantum well, that will improve the structure. And some other thing is we may introduce an electron blocking layer into the LED structures. That is, in semiconductor, actually the electron mobility is much higher than the Hall mobility, about several times difference. So that means actually if we don't have the electron blocking layer, the electron may go from the n-type material and go to the p-type material without go down into the quantum well structure. So sometimes we will have the very wide bandgap material, and that is to block the electron, and the electron will go into the hole for the light for the electron hole recombination for the light emission. So what we say is the quantum well that is along this axis, which means we can tune the composition during the epitaxial growth. But it is also possible for the quantum wire structure, okay? So looks like we have the quantum structure in this domain, or quantum dot structure, okay? So they can provide even better confinement. So for the emission characteristics, and we just said, for example, here is a band structure of the silicon. So you can see the minima of the conduction band and the maxima of the valence band. They are not in the same wave factor, okay? Not in the same K-space. On the other hand, for the gallium arsenide, the minima and the maxima, they have the same K-vector. So that results in a better emission characteristics. Okay, so that's it. The red band gap, that is the indirect band gap, and know that because when the photon goes down, they will release the energy, okay? And also, photon, the momentum of the photon is very small. So basically, we only, the vertical transition in the K-space is much preferred due to the momentum conservation, okay? So if we have the mismatch here, we may need another, for example, the defect to assist this vertical transition in K domain, in K space. So which means the indirect bandgap semiconductor, they have typically the emission characteristics much worse compared with the direct one. And here we will show you the radiative and non-radiative recombination, some basic idea. So when we promote the electron from the valence band to conduction band, and they want to go down from the excited state to the ground state, there are different ways to do that. One way is we can have the radiative recombination, so they will generate a photon, okay? The other hand is they may release their energy through the vibration, or we call that is phonon. So that is non-radiative, and we call that is radiative, okay? And typically, for the recombination, typically we need a one electron and one hole. So the recombination rate, typically we use the form as a B times N times P. B is a kind of recombination coefficient, and N and P is electron and hole concentration respectively. Okay, so this is an example here. We can have some radiative recombination, that's what we want. And there are some non-radiative recombination due to the phonon or due to some other high order process. And also, if our epitaxial growth is not perfect, as we said before, if there are lots of mismatch in the conventional semiconductor, then there are some trap, okay? So there are some non-radiative recombination due to the traps. So this is an example, okay? So if we cut the edge of the p-type semiconductor, so there are some surface. So remember that in chapter 3, we talk about the band gap of the material, I mean the bulk material, comes from the repeated structure, okay, of the atom. And at this surface, there's no repeated structure, okay? So which means they will introduce some trap here. So when we illuminate the semiconductor, we excite the semiconductor, they will emit some light, okay? So you will see from the side view, okay? Then you will see the emission here. But at the surface, you will see the light become dimmer. The emission intensity decrease, okay? Because the surface state, they will result in a higher non-radiative recombination, okay? So here's a model. We just use some results, and we will not go to the detail. Okay, so that's why we said the recombination rate. We can use the coefficient times the n and p. And remember that n and p, they are the function of x, function of the space. And we can have some approximation. I will not go to the detail. And we can have the radiative recombination rate, non-radiative recombination rate as well. Then we can have the generation rate. So that is we call the continuity equation. So the electron, the derivative to the time of the electron concentration equals to the generation, and it's these two terms are generation term, and these two terms are recombination term, and this is radiative, that is a non-radiative, and this term describes the current injection, okay? So we can do some calculation, derivation. Then what I want to show you is actually we can have the output power, okay? So output photon equals to this equation. And here external efficiency means the light extraction efficiency, which means you need to take light from your LED out of the air. Yeah, because there are some total internal refraction from the high refractive index to the low refractive index, so low refractive index, so this term is not equals to 1. And also determine to the h nu. H nu is the photon energy. Also A is the area, derived cross-section area. And this term, actually, that will relate to the current. Oh, here. So that will result in the current. So you can read the output power, optical power results related to the current current here. Also, the photon number is a constant, so there are 3 efficiency, okay? One is the extraction efficiency. We need to take out the photon from the device, inside device, outside the device, to outside the device. And E dot I is current efficiency. As we said, the homojunction structure, do you remember that? We said that maybe the hole from the anode inject into a device, maybe they will escape outside the device. So we need to have the heterojunction or double heterojunction or electron blocking layer structure like that. So this term is related to electron hole recombination. We need to have a higher E dot I, of course. It is possible to approximate go to the 100%, and also the radiative recombination. So which means we need to reduce the trap, we need to reduce the non-radiative recombination, and to improve this one. Okay, so that means the output is almost linear to the input. I mean ideally. Okay. Okay, so that is we define the efficiency of LED. There's an internal quantum efficiency, and also the light extraction efficiency and the extraction efficiency. So the definition is the number of photons over the number of electrons. That is the from the active layer per second over the injection current. So that the input electrons, that output photons. But remember that that is assume we can measure the photons inside the LED. Okay, and so it's different from the internal and external. That is external to the free space. So actually that is a measurable term. This one is kind of estimation. So the difference between the internal and external is a light extraction efficiency. Okay, so it's the internal times the extraction efficiency. And for the emission spectrum, actually consider about the parabolic form for the conduction band and valence band. Actually, there's a distribution. So the ideal case, the full width of half maxima is about 1.8 kT, and that is determined by the density of states and the Boltzmann distribution. And typically, if there are some, when we grow the epithelial layer, and there are some composition change, and sometimes that is larger, so maybe 2 kT, 5 kT or so. And here this figure shows the temperature dependence of the emission intensity. That is actually, we said when we increase the temperature in semiconductor, typically that results in the intensity decrease, because the higher temperature means more phonons, and the phonons, they will reduce they will increase the non-radiative recombination rate, and that is more severe issues for the smaller bandgap material. So that's more serious for the red one, and then not so serious for the blue one. So here shows a very simple, that shows an example about the white light LED. That consists of the red, green, blue LEDs. But for example, it's a backlight unit of the LCD. But when you operate for a while, then the heat will result in the increase. The heat will increase the temperature of the LEDs, and that will reduce the intensity, as well as we said not only the intensity change, but also the peak wavelengths or the bandgap value, they will slightly change with the temperature. So which means if you use the LED as a backlight of the LCD, actually there is a shift in temperature and intensity, so your white point will change as well. So there are some calculation, and you can try to solve this issue. Okay, so we said there are 3 factors to affect the efficiency of the LED: the current efficiency, light extraction efficiency, as well as the radiative recombination efficiency. So for the radiative recombination efficiency, actually we need to have a very high quality epithelial growth. And for the current efficiency, we can use some device structure to optimize that. And for the extraction efficiency, that is what we want to address here. The main problem is total internal reflection between the semiconductor and the air. Okay, so we can only have a very small escape cone, and the light can go out to the air from the semiconductor. So there are several ways to do that, one way is actually we can put the encapsulation, for example, the epoxy film. Epoxy layer with the dome shape, and we can have the no we can have the we can change the view the light emission angle here, and also we can broaden the escape cone. And the other thing we can do is remember that we need to fabricate the LED or epitaxial growth on the substrate, and some substrate, they are absorbing substrate. Okay, so which means the light emission will be the photon will be absorbed by the substrate. So if we can remove the substrate, or we can use other kind of transparent substrate, then we can double the efficiency. So that's great, right? The other thing is actually if we can increase the thickness of the epitaxial growth, okay, we can open up from the side emission. Okay, so as we can see here, in the beginning we have very small emission here, but when we do all kinds of the method, we can open up to the 6 directions like that. Okay, so there are some discussion here. I want to skip it right now, and we will come back later. And I will show you another 2 things. That is, one thing is efficiency droop, which means if we increase the current, and we say actually the efficiency should be the constant, because we say the light output is linear to the current. Okay, so when we increase the current, it should be the same. But we see some some decrease in the efficiency. We call that the droop effect. So there are some droop resulting from the current, and there are some droop resulting from the temperature, and there are some loss, some mechanism account for this kind of loss. There are some internal loss, and there are some electron leakage. As I said before, the electron has a higher mobility than Hall, so that will, when the current density is high and there are lots of the electron, so they may result in the electron leakage from different kinds of the root causes, and that will result in the efficient droops. Okay, so this is OJ recombination. They happen in some cases, but anyway, that shows you for the Hall, they have a lower carrier mobility, so they will go to the heterojunction. But for the electron, it moves very fast with higher mobility, so that is possible some leakage here. Okay, so I will go back to the extraction efficiency later, but first I want to tell you something about the epitaxial growth. So that is a very old epitaxial growth method, so I would not talk about that, but I will show you the MOCVD, that is a metal organic chemical vector deposition. That is the common practice used for the 3-5 epitaxial growth. And here, typically the metal organic source. Okay, so you can see it's a metal, aluminium, gallium, indium, and there are some metallic, there are some organic ligand. So that is called a trimethyl, because there are 3 methyl group connect to the aluminium. and we can have the different composition of X and Y and Z. And V here means the group 5. Group 5 may be the phosphide or the nitride, and we can deposit as the aluminum gallium indium phosphide or aluminum gallium indium nitride or indium gallium nitride as well on our substrate. So that is the very famous gallium nitride growth mode by Professor Nakamura, which was published in APL 1991. As we can see, it's trimethyl gallium, okay, with hydrogen, nitrogen inside, and here's the gas phase inside the chamber on the substrate, and they use another nitrogen and hydrogen push the flow, and so there are more interaction with the substrate. So that is one special design for the gallium nitride growth. And for the gallium nitride growth, that is very, very interesting. So typically we say for the conventional growth, we need to have the lower mismatch. And once we form some dislocation, and dislocation will continue. But for the gallium nitride, that's very interesting. That is if we introduce some dislocation first, and actually this dislocation will not grow, will not continue. Okay? So that is what we call the epitaxial lateral overgrowth. That means if we grow, then stop, then etching, like that. So etching means looks like we introduce some not perfect condition here, and from the narrow rod we perform the second epitaxial growth. Then they will combine together, and also there are lots of dislocation, but that's fine. We have fewer dislocation on the top. Okay. So as you can see here, we have some E-log. Okay. So E-log is for this log is here some narrow rod here, okay. And when we grow on this area, then we can see there are not very many dislocation. On the other hand, for the substrate without E-log, and you can see lots of the dislocation. And it happened. We can also do this kind of the thing in the substrate. So that we call the pattern sulfide substrate, or PSS. Okay. So that is normal practice right now. So we pattern the sulfide, and we grow the gallium nitride. Then we have lots of dislocation here, but interestingly, when we continue growth, then we can see the dislocation. There are not many dislocation on the top. And the other good thing is actually the size is about micron range. So they looks like the mirror, so they can improve the extraction efficiency of the gallium nitride LED. So that is the growth, the image without the pattern PSS. That is with the PSS, and you can see lots of defect in this image, but there's not so many defect here. And another thing very interesting for gallium nitride is actually when we increase the dislocation density, the efficiency does not drop so fast. Okay, so which means for the other conventional gallium arsenide, gallium phosphide material, it's very sensitive to the dislocation. But for the indium gallium nitride, that is not so sensitive. The region is when we grow the indium gallium nitride, that is not very uniform in terms of the composition. So actually it forms lots of the fluctuation. So there are lots of the localized states. So the the carrier, they cannot move freely. So which means they are very localized. So they will not diffuse very long, so they cannot see the dislocation easily. Okay? So that's a very special case. I would say, we would say, oh, the success for gallium nitride is lots of surprising. Okay? So that is a material part. So we can do the epitaxial growth by the MOCVD, metal organic chemical vapor deposition. Then we go to the device structure, and that is the two kinds of the structure. One is for the phosphide system, and typically we can fabricate on the gallium arsenide or gallium phosphide substrate. So that is a conductive loop, that's semiconductor. So we can have the vertical p-type and n-type configuration. On the other hand, for the nitride system, the sulfide material, that is insulator. So we need to put the n-type and p-type material on the same side. Okay, so that's the top view and side view for the phosphide material, phosphide LED and the nitride LED. There are different kinds of the configuration for the electrodes, because electrode is a metal. But of course, we can use ITO, but for the ITO, the conductivity is limited. For the metal, they have the much lower resistivity, and we can try to change the configuration to achieve better current spreading. And here shows sometimes we want to increase the thickness of the LED, so that we have the much more uniform current spreading, and we can tune the layout of our electrodes, so that in this case the hole from the p-type material, they may be not so uniform because the length is very long. And p-type gallium nitride, the resistivity is pretty high, so there's a voltage drop here. So we can move the electrode from the side to the center. So that's one way to do that. Okay, and then move to the extraction efficiency enhancement. As I said before, actually we want to open the 6 windows from the top, from the bottom, from each side. So there are lots of the design. But that is the design what we use. Actually, we can shape the die, okay? And also, we want to use gallium phosphide substrate. That is the wide bandgap substrate. Excuse me. So that is transparent to the emission wavelengths. Okay, there are lots of the invention, but not so. Some structure is maybe the cost is very high, but the efficiency is not so amazing. So that is figure I pretty like. That is improvement of the different geometry. So for example, here is it's a phosphide system, phosphide LED. Okay, so it's a ray emission. So in the beginning, that is absorbing substrate. So when you use the transparent substrate, then you can see in the line for the whole region. Then you can change the electrode from the one point to this wider region. So it becomes brighter again, and you can shape it, and you can have the higher flux. So from here to here, and from here to here is a 5 times improvement. From here to here is 1.5 times improvement. And that is so for the nitride system is the light emission. So the PN is at the same side. So sulfide is transparent, so you can emit the light from here and put the metal reflector at the top, or you can put the upside down. So right now the PN junction PN type is here, and the light emission through the sulfide structure as well. And also, because we have that is also possible to fabricate a gallium nitride on silicon. Okay, so for example, we have the silicon substrate and we can have the epitaxial growth, and that is also very promising way for the gallium nitride on silicon. That's for the 3rd-generation semiconductor. Okay, so we can do the encapsulation. Okay, so this figure shows you for the light stream efficiency ratio versus the encapsulating epoxy. That means the refractive index difference between the semiconductor and air is very large. But if we put the epoxy dome, then you can see we can increase the light escape cone. Okay, so when we increase the refractive index of the epoxy dome, then we can increase the light stretching efficiency. Besides the shape of the dome, we can manipulate the light emission patterns, as we said in the LCD chapters when it was used for the backlight system. So that is a common package we see. Actually, that is epoxy to protect the LED, and actually LED is pretty small, maybe 100 micron or so. And we have the cathode, and we can have the anode, and we have the epoxy, and that is provide the electrical path and optical path. And also for the lighting purpose, actually that will generate lots of heat. So we also need to consider about the heat thermal path. So we can use a thermal resistance to describe this, and we can dissipate lots of the power, and without increase lots of the temperature. Okay, so let's see the application, and you can see outdoor lots of LED display, and we just mentioned that as the backlight unit of LCD, which can provide much better color gamut compared to the conventional CCFL co-cathode fluorescence lamp, and we can combine with quantum dot and color sequential method that is possible, and as well as the okay, and also the we can use the mini LED to have the as the backlight as well. Okay, so another thing is the for the huge display, and as we can see here, you can see very large, but if we see very close, and we can see lots of the dot because the resolution is not high. So that actually that was first proposed by Sony, and then by Samsung also have lots of the product, maybe the product, but anyway, demonstration about that. So the size maybe that's not so huge, but they use they call the micro LED, or Sony call the crystal LED. So actually that's very small, and the aperture ratio maybe only 1%, but they can emit a very strong light, and the size is very small, so the quality is very good. And it is also possible to make it ultra small. For example, we can tandem, or we can stack the red, green, blue LED together. Okay, so it's a blue one, green one, red one together, and they can have very, very small for the purpose of the projection. Okay, so that is micro LED, another application of the micro LED. So one way to achieve that is the transfer from the one substrate to the the other substrate. For in this case, they transfer the red LED to the red LED epitaxial to the green gallium nitride epitaxial, so that you can see here's a red pixel and a green pixel, and you can change the current density. You can change the emission color from the green to the red, and in between is some orange or looks like a little bit yellow colors, so that it is possible to achieve a very small projector. As you can see here, that's an image if you wear this kind of glass. And also, another way, not to transfer the from the different substrate. This is a way by using the quantum dot. So they use a nitride to emit the blue, but they put some quantum dot on the top of the LED to emit the green and red. And so that is also possible. But there are also some issues until now. For example, there are some leakage line because maybe the quantum dot cannot absorb 100% of the light emission. So there's some light leakage. So that will result in some issues for the emission color. And also, as we said before, quantum dot has some lifetime issue when that is very close to the your light sources. And there are some other issues, many issues for the integration for this small display with some optics. But anyway, there are some demonstration, as you can see here. It's the 8x8, and there are some demonstration for the different monocolor or the full color displays as well. And also, it is possible there are lots of the interesting invention. For example, we can use this kind of the shape to bond the LED chip with the silicon circuit when we combine these two, and we need to use this kind of wafer bonding. And also, there are lots of the transfer skill to transfer the red, green, blue from their mother substrate to the other, for example, glass substrate or TFT substrate. That is one invention in the patent to pick and press your LED. So it's for the mass transfer. And this one is also is another kind of the pattern. So the LED is picked up by the electrostatic force, and that is put on the target substrate, and there are some heater, and there are some bonding there. So that is on the TFT array as well. So I think you see the Touch Taiwan, and you can see the plain nitride. They have a beautiful LED, micro LED demonstration. But when we shrink device, and actually, as you can see, that is for the different size. Although the current density increased, but you can see the very strong decrease in the efficiency. So, which is still an issue and open question when we have the higher and higher resolution, and the efficiency is still a problem for the micro LED. And this is some interesting figures, not only micro LED, and they can down to the narrow structure. So that's narrow LED. So that is possible, but there are still a long way to go. Okay, and for the narrow LED, because the epitaxial growth is on different surface, so actually there are they can have some non-polar epithelial growth in this kind of narrow LED. That in principle is beautiful, but it's still very difficult for fabrication. And also this figure shows some wearable LED, and they have some not only flexible but it's stretchable. Okay, and here are the design of the electrodes, so you can not bendable, flexible, but also you can stretch it. So that's stretchability. You can have some deformation in this kind of the LED as well. Okay, I think that is all for the display application. And for the lighting, actually, there are lots of the for the different kinds of lighting, and you can see anywhere. So I think I don't need to explain that, because it's you can see in the market. You don't have to know from the class. And also there are some slides talking about the lighting or so, but anyway, just for your reference. And in about 7 years before, and the lighting, the efficiency of the white light LED achieved over 300 lumen per watt. So it's a really breakthrough. Okay, so I think that is the chapter 5 LED. So thank you.